All right, so in this example, we're going to be looking at a Laplace transform for a piecewise function. Okay, and I could verify pretty easily that the Laplace transform should exist because, again, remember, we need our function to be piecewise continuous, which it's easy to show that this is. And then we also need to show that it is of exponential order, which is not difficult in this case. We're not going to do that here. We're just going to evaluate this Laplace transform directly. Now, how do we go about this? Well, the Laplace transform of our function f of t, by definition, is the integral from 0 to infinity of e to the negative st f of t dt. Now, this function is piecewise, so we're defining it by two different expressions depending on where t is. How does that translate into an integral? Well, this is going to look like the sum of two integrals where our limits of integration are determined by these restrictions right here. So this is going to be the same thing as the integral from 0 to 1 of e to the negative st times 2t plus 1 dt plus the integral from 1 to infinity of e to the negative st times 0, this guy, dt. Now this integral, the whole integrand is just going to go to 0, which means the integral itself goes to 0. And now I'm just looking at a definite integral with a finite interval that I'm integrating over. So this is very doable. This is just integration by parts right here. I can split it into two integrals if I want. I can write this way. Integral from 0 to 1 of e to the negative st times 2t dt plus the integral from 0 to 1 e to the negative st dt, just by distributing that e to the negative st in and splitting it. This is integration by parts. I would want to use integration by parts here, and if I did that, I'm going to get negative 2t e to the negative st over s, and that's evaluated from 0 to 1, plus 2 over s, integral from 0 to 1, e to the negative st dt, plus this integral again, 0 to 1, e to the negative st dt. Okay, like I said before, because integration by parts is calculus 2 stuff, and because we've already done a couple of examples where we worked it out using the full, u, dv, and everything, I'm just kind of jumping to the next result here, hoping that you can fill in the gaps. Evaluating this from 0 to 1, I will get negative 2 e to the negative s over s plus, now if you notice here, these two integrals are the same. They have different coefficients in front of them, 2 over s here, and I can think of that as a 1 here. But I can factor the integral out so that it looks like this, 2 over s plus 1, and then evaluate that integral. The integral would look like negative e to the negative st over s from 0 to 1. Okay, this will give me negative 2 e to the negative s over s plus 2 over s plus 1 negative e to the negative s over s plus 1 over s. And s here will be greater than 0. Remember, the choice of s being greater than 0 is important because we need to know that the integral existed in the first place. And there's always going to be some condition like that attached to our Laplace transform. Okay, moving on. So we're not going to do any more examples. We're just going to talk about one more theorem here that's important in the discussion of Laplace transforms. And this one concerns the behavior of capital F of s, which is the function that defines our Laplace transform as s goes to infinity. Remember, when we're evaluating a Laplace transform, the idea is to take a function of t, work it into that transform, and have that spit out a new function of s, right? And we've been dealing mostly with s as a constant. We've been thinking of it as a constant because we're always integrating with respect to t. But once we produce this function of s, we may want to know something about that function, now having to think of s as a variable. And in this case, we're looking at what we can say about the function that defines the Laplace transform as s goes to infinity. So if f is a piecewise continuous function, on the interval 0 to infinity, and if it's of exponential order, which would imply that a Laplace transform exists, then that function, capital F of s, that we get from our Laplace transform will have a limit of 0 as s goes to infinity. Now, going back to our table of Laplace transforms, we can verify this for all of the Laplace transforms we've found so far. 1 over s minus a, s over s squared plus k squared. Each one of these, if you were to evaluate the limit as s goes to infinity, would be pretty easy to see that the function goes to 0 in all of those cases. But what this theorem is saying is that even though we don't have an exhaustive list in our table over there, there's plenty more Laplace transforms that exist and we could find. The same thing will be true of all of them. The limit as s goes to infinity of all of them is going to equal 0. How do we show this? We're going to run through a quick proof here, then we're going to be done with section 7.1. So once again, we're assuming that f is of exponential order, which gives us the following. We have this constant gamma, which we're using in place of c in the definition of exponential order, m1, which is positive, and t, which is positive, so that by the definition of exponential order, the absolute value of f of t will be less than this expression right here, this exponential function, as long as t is greater than capital T. Okay, and because f is piecewise continuous, then we can once again split this thing into two integrals, and when we're doing the integral on the finite interval from 0 to capital T, we know that integral can't go off to infinity. It's going to have to be finite, which means it's bounded on that interval. Okay, so in other words, that implies that the function absolute value of f of t, not necessarily its integral, but the function absolute value of f of t is bounded by some constant, some positive constant, which we're going to call m2, which can also be written in the form of an exponential function, m2 e to the 0t. Okay, we're going to do this for the sake of some simplification that happens later. So if we let capital M denote the larger of these two m's that we've talked about already, m1 and m2, and if we let c denote the larger of these two constants, 0 and gamma, then here's what we can say. The absolute value of f of s, capital F, is less than or equal to, now remember, capital F of s by definition is the Laplace transform. So I could look at the Laplace transform of f of t, and as we said before from our integral properties, the absolute value of that entire integral is less than or equal to the integral of the absolute value of the integrand, which would end up looking like this. Okay? That absolute value of f of t right there, notice we've put two different bounds on the absolute value of f of t. We've said that the absolute value of f of t is less than or equal to this exponential function, but it's also less than or equal to this exponential function. So the choice of capital M as being the maximum of these two and c as being the maximum of these two is we use that to show that the absolute value of f of t would be less than or equal to just regular capital M e to the ct. It would follow directly from these two results. So putting that in here creates this next inequality. This is less than or equal to m, which is a constant, so we pulled that out, e to the negative st, e to the ct. Combining those and evaluating that integral using a choice of s that's greater than c, or so putting this restriction on s is greater than c, to make this integral converge, we get capital M over s minus c. Okay, now as s goes to infinity, because both m and c are constants, the denominator is going to go towards infinity, which shrinks this entire thing down to 0. And by our inequality property, if the absolute value of something is less than or equal to 0, it can't be less than 0 because that would make it negative, and absolute values can't be negative. So the only possibility here is that as s goes to infinity, if this is going to 0, then f of s itself needs to be going to 0. okay, because its absolute value is going to 0. So that establishes that theorem for us, and that's also going to wrap up section 7.1.